Yeah. So, hello everyone. Welcome all on Data Phoenix webinar. Today we will speak about vector database and how you can use it for multimodal search and for RAG. With us, Zain. He is developer relation engineer from um, uh, V- uh, sorry,
That's okay.
VVA,
VVA.
VVA. Yeah, and he will share his uh, presentation and his knowledge in this area. So I give him a microphone, and we will start.
Thank you so much. Really happy to be here. And I know that Dimitru shared that there were a bunch of signups for this. So hopefully we can have a lot of fun. I'm going to take maybe 30 minutes, 35 minutes to go through some material that I've prepared here. And then I'd like to just take questions and discussion. And I think that'll be the more fun part of the session.
Yeah.
All right, awesome. So my talk today is on multimodal search and RAG. So, and it's with Weaviate. Weaviate is an open source vector database. So I'll start off just by giving you a highlight of, oops, okay, my clicker wasn't working, but now it is. Um, I'll just kind of put the punchline right at the beginning just to show you what this whole talk is about, right? So by the end of this talk, you'll get an idea of how this type of app works. And by the way, this app is open source and free. So let me play it for you and then I can talk more about it. And so the main idea behind this app is that you're doing text search and you've got all of these different multimedia files that are coming up that match with your text query. Um, and so, like I said, this entire app is open source. It's not very complicated, but I'll talk about the technology that goes in behind creating an app like this. And the main point here is that uh, you you're able to do this search over any type of multimedia, right? So you need machine learning models that understand that type of media as well. So before I dive into this, let me talk a little bit about vector databases so that everybody's on the same page, and then we'll start talking about their multimodal capabilities. So vector databases basically take all of your data. So imagine this is all the files on your computer. You can have videos, emails, images, uh, text documents. They go through some machine learning model, some AI model, and the job of this model is to turn your data into vectors, right? So one data object maps to one vector object, and a vector is just a group of numbers here, right? So if you have 1,000 data objects, you'll have 1,000 vectors, one-to-one mapping. And the really cool thing about this mapping is that similar data objects. So if you have two emails from your boss, and then you have um, two pictures from your vacation, the vectors for those will be closer together, right? Because they are semantically similar, they mean similar things. That's why the vectors are going to be closer together, right? So every vector is one of these green dots over here. And the one thing you'll notice here is that similar concepts are located in close proximity. So the word chicken and the picture of a chicken have vectors that are nearby, whereas the word chicken and the word banana and the image of the apple are farther apart, right? So in this vector space that we have, closeness signifies semantic similarity, and uh, farther away objects, the distance signifies dissimilarity, right? The higher the distance, the more dissimilar the objects are. So one way to think about this is that your machine learning model is essentially classifying. It's taking every data object and it's telling you where it belongs in vector space, right? Like I almost think of this as a classification system in a library that tells you where a book belongs, right? So a book on philosophy will be in one location in the library, and a book on the arts will be in a completely different location. And so the way I like to think about a vector database is just a very gigantic library that can have billions and billions of books, and every book has its right spot, and similar books will be in a similar location. And the search engine is essentially a librarian who's able to take your query, the thing that you're interested in, and retrieve the top 10 or top 5 closest books that might be of interest to you in real time. And so this is the main idea behind a vector database. This is all the vector database is doing. When we want to perform vector search, it looks kind of like this. You take all of your objects, you index them, and you've got them stored in this vector database. Now you've got your library populated with all the books that you want stored in there. Then a user comes in with a query, some sort of something that they're interested in, and that query looks like this. Right? The query can be turned into a vector, and that red dot is the vector for the query. Right? In human understandable format, this is what the query might look like. It's just a natural language 3-word query. Right? Whatever the user is interested in, they can put into that search bar like I showed earlier. And then the act of vector searching is looking around in the proximity of this red dot to see which green dots are closest in meaning. And then those are the ones that you want to return to the user because that's closest to what they're interested in. And so in short, the vector search pipeline looks something like this. Right? You have your machine learning model that turns data into vectors. You take your data, you pass it through the model, vectors come out, you store that into Weaviate, an open source vector database, and then your query comes in, it goes in through the same pathway, and it turns into a vector, and that goes to your vector database, and the vector database is now going to calculate a list of candidates that are the closest to your query. And then you can send that back to the user. And so in short, one way to think about it is a vector database is basically like Google searching over your own personal data. Imagine you could index all of your personal data and you could Google search over it. And that's kind of what a vector database is giving you the power to do. This talk is more about how vector databases can handle a lot more than text. So a lot of what I've talked about up until now is just text data. You've got emails, you've got text documents, PDFs, and you're searching over those. But vector databases can handle multimedia content, videos, audio files, images, just as easily as they can text. So I want to demonstrate how this works. And this is the kind of the key behind how that app that I showed in the beginning actually works. So let's start off talking about what you need to understand multimedia files first. So if you think about language models only understand one kind of modality, which is language text. But if you step back a bit and think about how humans learn, humans actually, for the first couple of years, for the year and a half and 2 years of their life, humans don't speak a lot, right? A lot of the foundational knowledge that we built is through touch, smell, taste, these interactive capabilities. So kids don't really talk in the first 2 years of their life that much. So the foundational knowledge that we built is pretty multimodal, right? Um, and then on top of that, once you've got that foundational knowledge, you can build on top of with language, right? So language is almost like a construct on top of that foundational knowledge that we build in our earlier years. So the and that's kind of inculcated so deeply in us that we can reason across modalities, right? So if I showed you this video and I asked you, what does this sound like? Each one of you could get an idea of exactly what this sounds like. So you can infer information from one modality to the other, right? Even though there's no sound, you know exactly what this sounds like. Right? You can also get information and flow it between modalities. So you know exactly what this sounds like. You might even know exactly what this smells like and what it feels like. You can feel the kind of the ground vibrating as the train passes by, right? So humans understand with all of our senses, and we kind of use those senses to understand a data point from different perspectives. Right? And we'd like our machine learning models to be able to do this as well, right? We're seeing now where Gemini, GPT-4, Omni, all of these models are coming out. They're getting more and more capabilities. At first, we got the ability to pass in images, but now we can also pass in audio files, video files for these models to understand. If I played this sound for you, you could probably even tell what that sounds like. And so we can kind of flow understanding from any modality to any other modality. I can show you a sound and you can imagine what it sounds like, what the video looks like. You can have a text description of it. So humans are really good at this multimodal reasoning. And the argument here is that if we want a generally capable AI, if we want um, robots or better tools, they need to be multimodal as well. They need to be able to understand and reason between all of these different multimedia types as well. And so in this talk, I'm just going to talk about what multimodal models are. I'll give you resources that you can use to continue your learning into the world of multimodality. I won't be able to cover too much in 30 minutes, but hopefully it'll be a good introduction, and then I'll give you resources that you can use to pursue further. All right. So the main idea behind a multimodal model is that you want to start off with all of the different types of data over here, right? So this can be images, text, audio, so on and so forth. And you want to have some sort of machine learning model, some sort of encoder or multimodal embedding that will project all of these different senses or media types into the same vector space, right? And the thing that's important about the vector space is that similar concepts, so the image here, the description here, the video here, if these objects are similar in meaning, they should be closer together in the vector space, right? And so when we have a multimodal embedding vector space, we want similar things to cluster together and dissimilar things to be farther apart, right? And so the key point here is that if you see two objects in vector space that are closer together, that means that they're similar. Doesn't matter which modality, it could be an image and a text file and an audio file. And if you have objects that are farther apart, that means that they're conceptually different, right? And we want to train models that can capture this semantic similarity that we understand exists in the world. So the way we start this off is we can start off with specialist models, right? We all know about text encoder models. So Ada from OpenAI, there's all sorts of models that can take text and turn them into vectors, right? There's also image encoder models that can take images and turn them into vectors. Likewise, there's also audio encoder and video encoder models that work on their respective modalities, right? But notice one thing: even though the concepts on the left-hand side are all similar, the vectors on the right-hand side are all different, right? So if you even just look at the first dimension of these vectors are very different, right? And in fact, all the dimensions are different. And this is because all of these models are trained independently, right? So this model doesn't know about this other model's existence, and they don't know about each other. So there's no way that the vectors would be close together here, right? So what we have to do is we start off with these specialist models, and then we can come together and kind of combine them by training them, right? And how we train them is essentially by saying if the concepts are similar, you give it training data points. And if the data points are similar, then the vectors should also be similar, right? And you keep on doing this over and over across different concepts that you want the model to understand. And eventually you'll end up with a multimodal embedding model where similar concepts will have similar vectors. And so typically how you have to set this up is by creating lots and lots of points where this could be the anchor point. So this is a random example from your data set. It says he could smell the roses. And then you choose a negative example, something that's very dissimilar. The lion roared. This has nothing to do with the top anchor. And then you create a positive example, right? So this is something that is similar. So a field of fragrant flowers is similar to he could smell the roses, right? And then what you want to do is generate the vectors for each one of these, and you want to train this by pushing and pulling. You want the positive data points to come together, be closer to the anchor, and the negative ones to be farther apart. And you can do this over and over. And every time you do this, the model will learn about the difference between two concepts and the similarity between two other concepts. And so this is the process of fine tuning your embedding models. And you can do this for images, for text. You can do this across modalities as well, right? So here, for example, this is an example for doing this over images where you've got an anchor point, which is this image of a dog. This is a positive point, which is just the black and white version of this image. And this is a completely different image, right? So this is a negative. We want to push that apart and we want to pull the positive one closer together. And if you do this hundreds of thousands of times over, you'll tighten up your vector space where similar points will be closer together. And you can do this across modalities as well, right? Because you have the ability to turn any multimedia file into a vector, you can push and pull the vectors in vector space. So this is what you want to happen, and you want to do this thousands and thousands of times for any concept that you want to teach the embedding model about. Right? And so once you've got this training done and over with, you've now generated this shared multimodal vector space where you can imagine taking all of the data on your computer and you can embed it, and similar things will now be in close proximity. And now we can fall back on our vector space calculation that we talked about in the beginning. And so now if we have this multimodal embedding model, we can now pass in a query. And so this is something that you would, in the app that I showed, this is something that you would type in the search bar, right? So lions roam the savannas. And then this goes into your vector database and you perform this proximity search. And now because the media files are all bound together, similar things are in a close proximity to each other, you can get any of these out. Right? And this is known as text to any search. And this is the exact technology that I was talking about in the app that I showed earlier. But not only that, because this model can understand any type of media, you can typically pass in any type of file as input as well, right? So you could say my query is this image or this audio or this video, and you can use the video as a query, and you can get out anything that's semantically related to that input query as well, right? So this is known as any to any search because you can pass in any modality as input, and you can get out any modality as an output as well. Right? And so it's pretty flexible, and our machine learning models can now do this any to any search that humans are really good at as well. And you can flow kind of information from one modality to another, and you can do retrieval across modalities as well. Okay, so that kind of gets us the embedding portion of our that we need for our vector database. Right? The next thing that we're going to talk about is the language models that we've talked about are still, they only understand language, right? So if you can retrieve and search across all of these different media files, you also need your language models to be able to see them, right? You need your language model to understand audio, video, images. I'll talk a little bit about how you can teach language models to see as well, right? So typically what we do with language models is we pass them text in and they pass us text out. If you open up ChatGPT right now, you can pass in text and then it'll give you text out. What's new with GPT-4 Omni and a lot of these new models is that you can pass in an image along with a text, right? So you can pass in this image, you can drag and drop this in, and then you can say who drew this painting, right? And you can do this, and the output will be text. Right? So now we're going from just a text in, text out to a image text in to a text out. Right? And so to do this, we have to train our language models to see. And the way to do this is actually quite interesting. You start off with your two input modalities. You start off with the image and with the question or the text tokens, and then you pass it in to your language model. So typically, this is no different from what would happen normally. You take these text and you turn them into tokens one at a time. But what's interesting is you can take the image and you can cut it up and you can pass it into a vision encoder, and the vision encoder then turns this into vision tokens, right? So these are image tokens that can then be kind of thought of as similar to text tokens, right? And so this vision encoder turns pieces of the image, kind of square chunks of the image, into these vision tokens, and then you can concatenate those vision tokens along with your language tokens, and you can simply pass them through your language model. Right? And initially, the language model won't know anything about these tokens because it's never seen these, or it's never been trained on these because they've been generated through some image projection modification. But the whole point is to tune the model to learn about what these vision tokens mean. Right? So if you've got enough of these examples of images and text prompts, you can eventually project them into these image and text tokens, and then you know what the answer is, you know what the text token output should be. So you can actually train this thousands and thousands of times over. And when you do this, you'll get a language model that can actually see and understand images. And this is typically how a lot of the language vision models that you're finding in industry are trained to understand these different modalities. Right? So things like Lava language vision assistant model, Polygemma from Google is also trained in this manner as well. So this is the example. That this is a really cool model. It's a very small model. It's about 3 billion parameter model that uses the same architecture where you've got image in, text input, text in. You've got some sort of image encoder here. So here the image encoder is slightly different. They use a different loss function, but the main idea is the same. You take your image, you turn the image into image tokens, you take the text, you turn it into text tokens, and then you concatenate the tokens together, and then you give it to Google's Gemma model, which is a 2 billion parameter, really small language model. And then it outputs it, it gives you a text answer. The cool thing about this model is that you can really easily fine tune it. So the one thing that the creators had in mind was they left the last piece of training up to you, so you can actually take this model and you can tune it to be a expert at one text to kind of image to text task. Right? So one example of this that I read about was you can take receipts, images of receipts. This could be the input, and you can ask it, what items do you see on the receipt? What is the total for the receipt? And then you have some sort of text output. So this is a JSON of each line item thing that I have on the receipt is detailed here. And you train this. The good thing about this is that you can actually train it for around 500 to 1,000 times with different examples that look similar to this. And it'll get really, really good at extracting text out from your receipts and turning that into a JSON. It actually performs better than GPT-4 Omni at this specific task, and it's only a 2 billion parameter model. Okay, so hopefully by now I've convinced a lot of people that large language models are great, but large multimodal models, language vision models are even better. So now I want to talk a little bit about who's using these things in production. Right? Um, So the two use cases that we've seen at Weaviate for these language vision models and these multimodal embedding models, the first one is multimodal RAG. So RAG typically, so here I'll explain a little bit about what RAG is. When people are using language models, they're typically doing something like this, right? They start off with a prompt, I want to eat Malaysian food. What are good Malaysian places to eat in Toronto? Then you give that to a language model, and it gives you some sort of answer based on its weights, right? So information that's distilled in the weights during the training process. But this is pretty. Uh, this doesn't take into account anything that wasn't trained into the model, right? So typically, what people have done then is they give it relevant information that the model can read before it has to answer the question, right? And these can be any document. These can even be documents that the model was not trained on. Right? And then the response is customized to your documents over here. Right? So this can be my personal diary, and then I can ask it questions about the personal diary. And the language model was never trained on my personal diary, but now it can give me customized responses from that. Right? And so this is a very simple RAG workflow. But what we're seeing people do now is instead of just passing in text documents, so for now these are text documents and that's your Weaviate vector database, and simply going over and scaling this up to billions of documents and giving that to a language model. So now the vector database performs retrieval over these billions of documents, and now you take the relevant documents that come from here that are relevant to this prompt, and you stuff it into the context and you give that to the language model. What we're seeing now people are doing is they're actually retrieving multimodal content, right? So they're indexing images or they'll index video and text into a vector database. And now you can retrieve from this, right? And this goes into what I talked about earlier, where if you have a multimodal embedding model that can project all of these into a unified vector space, then you can retrieve an image that might be the closest to a prompt, right? Maybe none of the text is close. What is the most semantically relevant is an image. And now if you have a language vision model down here, you can take the text in and the image in, and you can get it to generate some sort of customized response. Right? And this is the main idea behind multimodal RAG, and a lot of people are experimenting with this, especially where they've got PDFs where a PDF can have text, but it also has graphs, tables, and figures. And so there, when you're ingesting the entire PDF, you get all of these different types of media files that you want to RAG over. Okay? And so the solution for that is to adopt multimodal RAG instead of just text-based RAG. A second application where we're seeing a lot of traction is in e-commerce. So especially for multimodality, typically in e-commerce, companies have not just text description of their products, but they also have images, video files, audio files of their product. And so they can take advantage of these multimodal assets to improve the recommender systems for their customers. And so typically, the reason why this is quite powerful is very simple to understand, right? If I ask you a very simple question like this, how would you answer this, right? You could give me a description and you could say, okay, let me just write down for you how this works, what type of burger I like. And this is typically how recommender systems have worked in the past. Or you could show me, right? Maybe you have an image of the perfect burger and you could say, this is the perfect burger for me. Right? Or you could tell me how it smells like, right? You like the sesame seed, the freshly baked bread. You can describe that smell to me, right? Or you can describe a crunchy sound to me, right? So the reason why this is really powerful is because now the customer can identify exactly why and how they like a product. And that then becomes the customer's identity, right? You can use that modality to capture what a customer likes and what a customer dislikes. And the cool thing now is because we can capture these different modalities into vectors, and we can even there's work that's even going into capturing tabular data, tables, and kind of the caloric intake for different menus into vectors. We can capture the perfect kind of preferences for a customer into a vector or even multiple vectors here. Right? So maybe you have one image vector, you've got a text vector, and then one nutritional facts vector. Right? And you can do recommendations based on all of these or maybe just some combination of these. And this is what we're seeing customers build trials with and deploy. There's also larger companies that are actually using this in production right now. So Amazon and Facebook are actually using multimodal recommender systems in production for their marketplaces. And the reason why this is quite powerful is because it allows you to uniquely identify what a customer likes, because now you have more senses to do this with, right? You can recommend a product based on sight, based on text, based on video, and before we couldn't do that. You can also uniquely compare relevance between products, right? Because you can compare across modalities. You can compare a product description to another product's look. And then it's also easier to tell the difference between similar products. If I describe to you two products that have the same function, you might not be able to tell them apart. But if I show you their images, you can tell me exactly how they're different, right? You could say, oh, this one is colored differently, or this one is posed differently. Right? And to kind of put this, uh, to make this a little bit more concrete, I'll show you an example from a paper that Amazon published where one of their users was interested in this sofa, right? And they if they just use text, it comes up with recommendations that look like this, right? And these are all functionally the same. These are all things that you sit on. They're all furniture, but they're not quite like this product, right? So you could think that the description here is similar to this product, but the visual aspect of this, that the image embedding, is not very similar at all. Right? So then what they showed in this paper is that if you take into account the image vectors, the image modality as well, the recommendation is much better. Right? So notice here now you've got your image recommendations now, where not only is the description similar, but also the look and the pose of the product is also similar, right? And a customer is much more likely to buy some of these than they are to buy these, right? Because these are very close to what they wanted. And this is the power of doing multimodal recommendations. And so with that, I'll end off. The last thing I'll maybe talk about is if you're interested in this, we're going to be holding a quite a large workshop that's coming up next week, where I'm going to dive into the advanced tricks for RAG, and I'll break down different components of RAG. So if you're interested in this, please do sign up. And that's the QR code that'll take you to that page. And if you want to learn more about this, we actually made a whole course around this for you. So you can also look into this. That QR code will take you to the course. Um, this lecture is actually just built, it's a small slice of that course. So you can have a look at it if you're interested. And if you have any questions, we'll take those now. And if you have questions later, feel free to connect with me on my social platforms. Thanks. Throwing it back over to you.
Thanks for this overview. So, yeah, if you have questions, please ask them under the video using Slander. We will answer for them shortly. And also, I have some questions from my side. So, let's maybe come back to the history and speak about some uh, about history of vector database. When you start working with vector database, what was the start was state of the art, and how all is changed for now?
Yeah, that's a good point. So I started working with vector databases 2 years ago. Um, and initially, I didn't know what a vector database was. My background is in machine learning, and I've been in the field for 9 years. So I knew about representation learning. I knew that you could take data and you can turn it into vectors, and you could use things like autoencoders to kind of project data into latent space. I knew about all of that, but I didn't know that you could actually scale this up and take billions of objects, turn them all into billions of vectors, and then you can now say, oh, this vector is similar, so this must be similar in the original before we turned it into a vector. So 2 years ago, a lot of the applications for vector databases, so this is pre-ChatGPT, um, a lot of them were mainly around semantic search, right? So if you're
Mhm.
building some sort of website and you want to index your data and you want to give your customers the ability to search over all of your catalog or your documentation or something like that, you could use a vector database to power that search engine. That was the main value prop behind vector databases. A lot of the technology around it was quite similar, actually. You take a machine learning model, you embed your data, and then you search with it. And a lot of that is very similar still. But post ChatGPT, a lot of the reason why people know and use vector databases now is to help a language model. Right? And so the search component is still there, but they take the results from the search and they give it to a language model to kind of read over and give you relevant answers rather than giving the search results to a human and the human just does whatever they want with them. Right. So that's the main change. I think in terms of the engineering and the technology, I think there are small changes here or there in terms of um, how we're dealing with vectors, how we're quantizing vectors, we're making it more efficient, decreasing the cost. But those are all kind of smaller details in terms of a vector database. The main use case of how you're using machine learning models to capture the meaning behind data is still the same.
Yeah. Today, vector database is very popular, and companies start to use it. What challenges they see and start to facing when they start to integrate vector database in their system, and also RAG system, because it's very often
Yeah,
part of
yeah.
mm,
So
their
oftentimes
solution.
companies have, yeah, sorry, go ahead.
Yeah, yeah. Go
Yeah.
ahead.
So typically companies have some form of pre-existing database, so either a SQL or a NoSQL database, and then when they're thinking about vector search, a scalable vector search, they're thinking, how do I take the components that I need to vector search over, get them into a vector database, and then how do I maintain that? How do I scale that up? So typically, when you're doing a proof of concept, it's quite simple. You don't need a scalable solution. You can take 10,000 objects and you can do brute force search, and that will be real time. I think the main trouble that people are having now is when you want to take the proof of concept and actually scale it up and put it into production. Now you want to scale up from 1,000, 100,000 objects to maybe 10 million objects or 100 million objects or a billion objects. That's where brute force search doesn't work anymore. And you need more dedicated solutions that can do vector search at scale. Right? So this is the main problem that people are seeing. In terms of, you asked about particularly RAG, I think that's a good segue. So this is one of the questions that I'm going to be talking about in the workshop that we have coming. But the main problem that people are having with RAG is, how do you properly index your data? So I've got 400 pages of PDF. How do I chunk it properly, right? Do I
Yeah.
chunk paragraphs? Do I chunk 250 characters? Or should I use some sort of document structure? How do I chunk the images? How do I even index the images with the text, right? There's all sorts of challenges where it's not clear and there's no correct answer. It depends on the domain, right? The other thing that people are having trouble with is, how do you increase the relevancy of the objects that are coming back, right? If you have if you're indexing a textbook on chemistry and the user queries something, how do you make it not return irrelevant search results, right? What are the kind of the small modifications and the tunings that you can do to make the output from the vector database relevant, right? And so there's a whole kind of slew of techniques that you can play around with. Um, and there's also other aspects that you can use. You can use external models to make the output of the vector database even more relevant. So oftentimes, how these problems manifest are just in the form of hallucinations, right? You might be running vector search and the things that are coming out of the vector database are completely irrelevant, and you give that to the language model thinking that you're giving it relevant things, and the language model gives you some incorrect output, and you have no idea where in the RAG pipeline something broke. So typically, when you're thinking about the RAG workflow, you kind of have to think of it at least as two separate components: the search component and then the generation component. And then even within that, you can break them down further, but then at least you have a way to evaluate if the RAG output is bad. Is it because the retrieval part is bad, or is it because the generative part is bad? Right? And then you can run evals to measure that. But those are typically the challenges that people are having um, on a high level, and then it varies
Yeah.
greatly depending on the product and the data set that you're building with as well.
Yeah, the challenges with tokenization, I think it's very critical and very often company and developers have. So maybe you can share your expertise and yeah, some cases how to better uh, to tokenize and split different type of data. For example, text, how to better videos,
Yeah.
audios, images.
Yeah, that's a good point. So typically for text, um, So I think probably the best way to start off is to take advantage of unique characters that are in the text, right? So if you're splitting HTML, use special tags that are in the HTML to split the text. If you're chunking Python code, use the existence of specific keywords to chunk the text. So you can use document based chunking. And so you take advantage of the structure of the text so that you're not cutting things in the middle. You can also use language models to chunk for you, right? So you can give the language model your chunk of text and say, where should I break this so that I don't lose like a train of thought, right? And that's also another way to do it. It's more expensive, but it shows the best results. um, when we talk about chunking multimedia, this is quite interesting. So if you're thinking about images, you're typically not chunking images in the same way that you're chunking text. A lot of the times when you're chunking images, or let's just call it pre-processing images, what you have to do is worry about kind of cleaning up the image. You might want to do background removal. If the object that you're interested in matching with is in the foreground, then you want to do background removal because the background might throw off the semantic search or the vector that's generated. right? You might also want to clean up the image. You might want to take some sort of augmentation of the image where you reflect it and you say that this vector is the same as this other vector. Right? So you could use all sorts of different pre-processing techniques that are classically done in computer vision, and I think that would also help. The video question for chunking video is actually quite interesting. So depending on how your model works, typically a lot of people what they're doing is they're using image models to encode video, and what they'll do is they'll take frame by frame of a video, and they'll generate one vector per frame. Right? And typically a video is pretty sparse because if you look at, let's say you have 30 frames per second or 60 frames per second, you don't need to encode every single frame because there's no movie that changes 60 times in a second, right? So maybe you can downsample and take like 3 frames per second, encode them, and then save as a property or a metadata the timestamp, and then you can perform image search over the frames of your video, and then extract out which frames are relevant and how long they stay relevant for. Right. So if you've got maybe 15 seconds of relevant frames, you know that that snippet is important. Right? And then you can also use this downstream to chunk your video. You can take kind of frames of a video, and as long as they're similar enough, the vector embeddings for them are similar enough, you know that they should belong in the same chunk, i.e., they're in the same scene or they're in the same part of the movie. Right? And the minute the vector changes, you know, okay, this is the next chunk. Right? So this is kind of a level of video semantic chunking that you can do as well.
Yeah, and if you speak about also some recommendation system, maybe you have some specific recommendation for recommendation system, how to split this data, because in recommendation system we very often have some description, some photos, some videos, and it's all about our one item in our store. So
Yeah.
maybe something specific to this one.
Yeah, definitely. So, especially for recommender systems, I think if you're embedding images, I think it's fairly important to do like background removal, to get rid of the noise in the image and make sure that the only thing that's part of the image is the thing that you want the vector to be generated from. Right? So that's just a pre-processing step. In terms of multimodal recommender systems, I think there's two ways that you can implement it. One way is you can turn, let's say you have a product, you have a description for the product, and then you have an image for the product as well. You can use
Mhm.
a model that understands both text and image, and it's bounded together to generate two vectors, and you combine them. Right, so now you have one vector that is some maybe 50% of text and 50% of image. Right? So now this vector is an image text vector, and you can do recommendations on the image text vector. Right? Um, so you can kind of fuse the vectors and then do multimodal recommendation that way. Another way to do multimodal recommendation is to keep the two vectors completely separate the whole time. So your image comes in, it gets turned into an image vector. Your text comes in, it gets turned into a text vector, and now you've got two separate vectors. And anytime a user clicks around, you can do recommendations. You can do a ranking of all of your products based on the images, and then a separate one based on the text. And so now you've got two rankings of the same products, and you can decide how you want to combine them, right? So you might have some sort of rank fusion algorithm that says if the product is a cloth, pay more attention to the vision vector or the vision recommendation. If the product is food, or if the product is something else, pay more attention to text. And so you can have your own rules or heuristics based on what products are often recommended or should be better recommended through vision, and which ones should be better recommended through text. Right? So those are two ways that you can break it down.
Yeah, and more one challenge which you told, it's the volume and growing the volume of data. So when you start to scaling, what strategy to for developers and for DevOps teams you can recommend to solve this problem? How to solve
Yeah, so typically if you've got lots and lots of data, and it's streaming in, you typically want to have some sort of data pipeline where you've got something like you're using some sort of Spark job or Apache Kafka kind of live stream of data, and then you've got a connector into the vector database, right? So as you're streaming in data, it's going into the vector database and you're populating it so that your recommendations can stay fresh and up to date with new things that you've put into the database. So that's one aspect of it. If you've got a catalog, or if you've got data that's growing over time, you want to live stream it into the database. The other aspect is also uh, typically, if you've got for e-commerce, you've got hundreds of thousands of products, you've got millions of users. You want to do really quick recommendation. There, you want to yeah, use a dedicated vector database, right? Because e-commerce is one of those applications where you have to do vector search at scale. And so there you want to use a dedicated vector database because it has all the machinery to scale up, right? It allows you to perform approximate nearest neighbors at the multi-billion scale. So there, your recall will be okay, and the latency will be really high. Sorry, the latency will be really good, as in it'll be low. The last thing you also have to worry about when you're scaling up is as the object count increases, the memory usage will also get really high, right? Because when you're performing vector search, typically you're building some sort of index, and because that index needs to be referenced and searched over quickly, it has to be stored in memory. It has to be stored in RAM. And so uh, if you're storing billions of objects or billions of vectors in memory, the costs can blow up. So typically the problem for DevOps teams is they'll have a really good, really fast recommender system that's able to serve the job well, but the cost will be way out of hand, right? And so if you're having that problem, then you want to look into quantization efforts, right? So with
Mhm.
quantization efforts, what you're doing is you're taking the vectors that you're storing in memory and you're reducing them in size, you're compressing them, sometimes even by a factor of 32x. And so there's a whole kind of zoo of quantization techniques that we've implemented in Weaviate that you can use and configure. And so if you're having problems with kind of cost, then you want to look into quantization. And there's a whole set of blog posts that I've written and talks that I've given around quantization that you can look into. We also have really great documentation around that. So those are, I think, on on a large scale, two or three problems that DevOps teams might have with scale.
Yeah, thank you. Let's look at some questions from our participant. First questions continue our discussion about tokenization. So, what good encoders and embedding methods you have tried, and you can recommend what their
Yeah.
pros and cons.
Yeah. So there's always the classical clip model. So typically, people start off their multimodal journey with clip, where you can it understands image and text, and those are the two modalities that you can use to embed with it. And you can do this image to text retrieval or text to image retrieval with clip. Um, so that works well. Uh, an even better one that I've played around with is called Image Bind from Meta from Facebook, and that one is the one that I used in the app that I showed at the beginning of this talk. That one understands image, video, audio, text, and then a couple of other modalities. That one is really good as well. So a lot of the concepts that I talk about in this talk are actually from the paper that they published. So if you're interested, that's called Image Bind. And you can Google Meta Facebook AI Image Bind model. That's a quite powerful one. It is bigger than Clip. Um, that's a good one. And then so those are the two that I would recommend. Those are the two that I've played around with. There are also multimodal embedding models on the that Google offers. So they're Palm model, multimodal embedding models. I've also played around with. Those are the ones that we use in the course that I mentioned at the end of my talk.
Mhm. Yeah, thank you. Next question: would this not create concentration along a particular cut of the data, which may actually hunt when another cut is needed. Or
This is
uh,
referring to some part of my talk. I'm not sure which part of the talk this is referring to. I'm not
maybe in the start of your talk.
particular cut of the data. Yeah, maybe they can expand because I don't understand what they mean by a particular cut of the data. I'm not sure if they're talking about the multimodal component part of the talk or the when I was talking about vectors.
Mhm.
Maybe we
Okay.
can go to the next question, and if
Yeah.
they give more details, then
Yeah.
then
It's
we can for sure
we
take
will
it.
come back.
Yeah.
Okay. Is it possible to build a graph rag using V-Wave only?
Yeah, so GraphRag is an interesting. It was an interesting paper from Microsoft, and they recently open sourced it. Um, I believe so. In GraphRag, I believe what they do is you take a large corpus of text, and then you ask a language model to extract out the knowledge graph of connectivity from within the chunks, and then you do this over the entire corpus, and what comes out are these nodes and the connections between them through relationships that have been established by mentions in within chunks. Um, you can build it using a vector database. So you can have Weaviate, and then what you would have to do is within Weaviate there are references between objects and properties. So what you would have to do is take the graph concept, and then you would have to turn that into connections between objects, and that's one way to do it. And I believe if you look into the source code for GraphRag, they have an implementation using vector databases as well.
Mhm. Thank you. Are there any well-established pros and cons of using the same index uh, for different modalities, uh, y- as other side using different indexes?
Yeah. So I think I'll restate the question. I think the question is more: are there any pros and cons for using a unified embedding model, one embedding model that understands all of the multimedia content versus using uh, separate embedding models, one for the text, one for image, one for video, one for audio? Um, I think the advantage of using one that's unified is that you can do this any to any search, right? You can pass in as a query an image and then get out text. You can't do that if you don't have a unified embedding model. If you have one embedding model that only understands text, you give it text, you will only get text back out. There's no way that it can retrieve for you images or audio files, right? So I don't know if it's an advantage, but depending on your application, depending on what you need to accomplish, it might be a deal breaker, right? If you want to perform text to any search, then the embedding model has to be able to embed text in with all of the other modalities. And so if that's something that you need to do, then you have to use an embedding model that is unified across all these modalities for sure.
Um, Thank you. Next question about recommendation system and not lost some data of user interests. Um, hmm,
Yeah, so in the recommender system example, are there ways to ensure that combining different vectors from user interests, meaning both are not lost? Yeah, this is a great point, by the way. So there are ways to do this. So you can do this based on filtering. Right? So you can have different products, and you can say if a user is clicking on different products, you can say one category, you can filter based on category. We don't want to add the fact that they clicked on cake and jeans, and we don't want to recommend off both of those. You can have some sort of filter that says, as long as the category is the same, then go ahead and combine and formulate some sort of recommendation. But if now they're clicking across categories, don't combine them. And then you can decide on what level the categories are different enough to not do recommendations on top of. The other thing that you can also do is to separate based on timestamps, right? So if you've got clicks that happened a month ago and now the user logged out and they log back in a month later, you don't want those old clicks to influence the new recommendations based on the new clicks that are happening, right? So you can bias the recommender system based on freshness, whether it's part of this browsing instance or whether it's an old browsing history, or also based on the categories that they're clicking around in, right? So you can have logic that uh, gets around this. But if you don't do that, this is a great point. One of the recommender systems that I built, the POC that I built, I didn't take this into account. And then when I was clicking different category of objects, um, it was combining them, and then it was recommending to me random things because the combination of a sneakers bar and a mouse is not a very good recommendation. Right?
Yeah. Thank you. The next question about create multimodal recommender system for YouTube channel. User can describe what kind of content they expect or visualize.
Yeah, so this is
So
definitely
is it possible
possible.
to?
You
I
can
think
so you
it's
yeah,
I think YouTube do something like that when it
yeah,
recommends
for sure.
you.
And
Yeah.
this is interesting because it's not just multimodal, because you can take um, you could start off just with text, right? Maybe take the
Yeah.
title of the video, the description of the video, start off there. That will get you a long way, and then take into account like metadata around the individual creators, the people that are creating the videos, and then you can even take into account maybe the thumbnails of their videos. And then you can start to add multimodality, right? Because when you start building a multimodal recommender system, there's so many things that you have to worry about that you want to incrementally add to the complexity.
Mhm. Yeah. Next one question. Can multimodal retrieval system retrieve relevant content complete, compressly of two different modality like both image and text?
Yeah, so let me interpret this question in two ways. So one way that you can interpret this question is, if I pass in one text, can I get back text and image? And the answer is yes. So if I pass in a text, if the most relevant thing is another text object and another image object, it can retrieve that for you. Right? Another way to interpret this is, if you pass in one second, let me think about this. Mm, yeah, so if you pass in any type of modality, so if you pass in image and text, can you combine them together, right? You can actually, if you've got an embedding model that can embed both text and image, you can technically do vector space arithmetic, where you can say this is the text vector and this is an image vector. I want to add those two vectors together and then retrieve whatever is close together. If the embedding model is unified, if it understands all the different modalities, you can do both of these examples that I talked about.
Yeah.
If you're interested in
Thank
this,
you.
you can actually read the. There's a paper. I'll type in the chat here. Um, Oh, I can't, but it's the image bind paper. They talk about this example where they pass in a video file, no, sorry, an audio file and an image file, and they retrieve back out another image file. So they should talk about this particular example in the paper.
Yeah, you can share the link with me, and we will share in our Discord. Or you can join to our Discord and continue discussion about this webinar. So, in any case, we will publish the recording, and I think we will have additional questions. So, it will be good point to continue discussion in our Discord channel.
Yeah.
Next question about best open source multimodal rack system. What do you know about this
Yeah.
system?
So
What,
good
what
open
you can
source. So
recommend?
one thing that I would recommend is part of our team actually built an open source RAG system. It's not multimodal right now. It's only text for now, but we are adding multimodality to it. So if you go to verba dot weaviate.io, let me share my screen here as well, so you can have a look. Um, let's see. I'll just share my screen. Uh, So here, do you guys see my screen? Yeah. So
Yeah.
here, if you go to Verba VV8IO, this is a open source RAG system that we built, and you can actually get access to the code here, right here. Um, so this is completely open source. You can fork this repo. There's a lot of people that are building with this. The really cool thing about this is that so this has a chat interface. You can dump your own PDFs into this, and then you can ask questions. If you go online and you get access to this, we've just put in our own documentation and our own blog post into this, and you can ask it anything about Weaviate. But the cool thing about this that I wanted to show you guys here is that we have a release log here where we're planning on adding all sorts of interesting things to this, right? We're going to add multimodality. We have an entire backlog of features that we're planning on adding to this. So this is kind of a live POC that we'll keep on updating, and we're also planning
Mhm.
on adding the multimodal component that you asked about over here.
Yeah. Uh, Thank you. We have more question about vector database. Is there some hybrid free database so we can experiment with? I think it's about vector database, but
Yeah,
what's in mean hybrid?
yeah. So so let me interpret the question, and maybe if it's wrong, they can correct me. Um, I guess the question is about vector databases that can natively perform hybrid search. So, if I'm understanding this correctly, you're asking about vector databases that can do both keyword search and vector search, and then do some sort of rank fusion combination of keyword and vector search. Weaviate actually natively supports hybrid search. So, anytime you pass in data into Weaviate, we build a vector index, but then we also build a inverted index. We use the vector index to do approximate nearest neighbors vector search, and we use the inverted index to perform keyword search. And you can just change one line of code. You go from vector search to hybrid search, and all of that is already implemented in Weaviate. So you can try that out. Um, if you go to our documentation and you go into uh, the search bar, uh, sorry, not the search bar, the drop down for different ways to search with Weaviate. I can also share my screen here if people are interested. So here, if you go into the docs and if you go how to search, uh, if you go to hybrid search, this will tell you how to perform hybrid search, and it's literally just one line of code change to go from vector search to hybrid search.
Yeah. And one of the last question, if we combine different vector database and take same problems which they solve, so which problems Viviate solve better that other vector databases?
Yeah, that's a good point. I think if I had to name three things that I think customers uh, really like about Weaviate is that first of all, this hybrid search functionality. Um, because we've built Weaviate with hybrid search in mind, when you pass in data, we're building both the vector index and the keyword index for you. If you're using a vector database that doesn't build this index for you, you kind of have to maintain this inverted keyword index yourself, the document word index yourself, and that's a pain to do. Whereas in Weaviate, it's already maintained there, so you can just access it. I think hybrid search would be a really promising use case. Another aspect of it is the ease of use. Right? If you're using vector databases for the first time, you might not know what the best embedding model is. You might not know how to integrate a language model to do a RAG setup. We have a module system where you can simply turn on an embedding model, and then you can pass in only text data, and we will vectorize it for you. So you don't have to come with your vectors. You can come with your data, and Weaviate will vectorize it for you. So it's very easy to use. And then the third thing that I would say is around scalability, right? So we're one of the best vector databases when it comes to scale. And we have customers that are using it at the multi-billion object scale for pure vector search as well. Right? So I think those would be
And
the three main strong points.
and these three features are available in open source version or only in commercial version?
No, they're fully open source. So Weaviate is a fully open source product. Everything that the entire code base between the open source and the managed version is exactly the same, right?
Okay.
So
Yeah,
yeah,
it's good. Yeah. So the last my question is about the future. How you see the future of vector databases?
yeah. So I think, of course, the technology behind vector databases will always keep changing. It'll always keep getting better in terms of speed. The costs will keep coming down. You'll be able to scale up, improve the recall and relevancy by doing all sorts of interesting integrations with machine learning models. Um, but I feel like the future for vector databases is really in owning the AI component, right? Typically, when people are building with a vector database, they're building an app that has AI at the core technology. And so I think in the future, the question will be, oh, are you building an AI app? Okay, then use a vector database. Are you building a more traditional classical app? Then maybe a vector database is not what you want to use, right? So I feel like that's where the future is. If you're building with AI as a core aspect of your product, then a vector database that is AI native should offer all of the integration, should offer all of the ecosystem. You should be able to talk to all of the other models out there, the language models, the encoder models, easily, and those should be kind of first-class citizens in the vector database. I feel like that's where, on a high level, the vision that we're pursuing with Weaviate being an AI native vector database is. Outside of all the engineering improvements and the research improvements, I think the larger vision, that's where we're headed.
Yeah. Good. Thank you for this cool presentation and this cool discussion. I hope it was useful for all our participants. Thank you for participants that was with us, and yeah, mm, see you
Thank you so
all
much,
on the
everybody.
next. Yeah, see you all on the next webinar. Thank you.
Bye. Have a great day.
Bye. You too.